Hello Vanguards. Today we'll be doing numbers 5 and 6, and we might even get to number 7 too. So today we're going to start off with the hydrogen-oxygen combination. So we're really going to do 2 labs for the price of 1. So the first thing we'll use is some stuff called zinc. And so zinc is obviously a solid. If you look at the back of your periodic table, back here in the middle part, you'll see the activity series, and you can start thinking about zinc. So the zinc that I'm going to use is called mossy zinc, and it's kind of like the leftover stuff when they're using zinc, and the U.S. uses hundreds and hundreds of tons of this stuff for lots of different things every year. So we'll be taking some zinc and we'll put it into an Erlenmeyer flask. Just put a little random amount right now. When we get to stoichiometry, we'll be measuring that out and we'll figure how much we're going to make. So we got the mossy zinc in there, and it has a lot of surface area, so it should react pretty well. And then we'll also take some hydrochloric acid, which is an aqueous compound. It's dissolved in water, it's clear. We'll add some of the sulfuric acid. Maybe you can even hear it. And you can see those bubbles that are being made. And we're going to catch those, whatever the bubble stuff is. Actually over here, I've got a reaction that's been going for a while, alright, that we'll use. Alright, so let's just talk about this first reaction. So we've got zinc. It's just solid zinc. It's shiny, it would conduct electricity, it's a solid, it's got lines of zinc cations in a sea of free-floating valence electrons. But for this reaction, we just have to think of it as zinc Zn, and it's a solid. So we'll add some hydrochloric acid, some HCl, and that's dissolved, it's aqueous, it's very strong stuff. When you look at the back of our periodic table, you'll see that we've got Larry lithium over here, super active, and Gary gold way over on this side, not reactive at all. If we find zinc, there's zinc right here. So zinc is about in the middle, so it's medium reactive. And then here we've got hydrogen, which is actually acting sort of like a metal here. It's behaving like it's on the left side of the periodic table. It's written first. So it's bonded to chloride. And so if we look for H as an acid, we see it's down here. It's not as active. Now right now hydrogen has a partner, but zinc is more active, so it's going to take the place of H. And so we'll end up with Zn bonded to Cl, and we'll have H all by itself. Now there's a couple little problems here. When you have zinc bonded to something, you know from your flashcards that it always ends up with a +2 charge. Even though it's in the middle of the periodic table, we shouldn't know what it is. Zinc always gets a +2. Chloride is way over from the right side of the periodic table. It's next to the noble gases. And it gets a -1, so if we crisscross applesauce, we put a 1 here and a 2 there. We don't write 1s. Alright, there's our formula. I can see through it. There's some little bits of zinc and impurities that are floating around in there too. But that's an aqueous compound, AQ. And then the other problem that we have right now is that hydrogen is here by itself, and that's one of the lucky 7. Hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine. Those are, if they're by themselves, they form buddy partners. And so that would actually be a gas. That's the stuff that's bubbling out. There's our first reaction. What kind of reaction is this? This is a single replacement reaction because zinc and hydrogen are fighting for chloride. So the bubbles are made out of hydrogen gas, H2. And do they react or don't they react? Perhaps you've heard some stories about hydrogen. There's a big dirigible a long time ago, 1920 something. It was called the Hindenburg, and they put hydrogen gas inside of it. And so hydrogen gas is very lightweight. It only has a molar mass of 2. So a mole box, 22.4 liters, only weighs 2 grams. That's very light. It's way less dense than air, and so it rises. So if you put that stuff in a balloon of some sort, it's going to rise really, really quickly. And so that was a great gas to put inside dirigible, or was it a blimp? So if you look over here into this little tub, we've got our zinc and our hydrochloric acid inside of here reacting. We got some sort of gas coming out of there. I think we figured out what kind of gas it is. And we're making bubbles. Perhaps you can see the bubbles coming out there. Got a bunch of bubbles. And what I'm going to do is I'm going to see some of the properties of those bubbles. There they go. And I'm going to hide back here just a little ways and see if anything happens. Yep. So what do you suppose that reaction was? Well, you know that for things to burn, they need oxygen, and you know that oxygen is a very reactive compound. So if we take the H2 and we react it with oxygen, which is found in the air, we should be able to make some sort of compound that has H and O in it. Well, not surprising that that compound would be H2O. And so we took hydrogen gas, G, and we took oxygen gas from the air, and we made water, which was pretty darn hot when it was made, and so that was probably a gas at that time. So there's our reactions. This first reaction was a single replacement, zinc fighting with hydrogen. The second reaction was hydrogen plus oxygen, two small things making one big thing. So what kind of reaction is that? Two small things making one big thing. That's a composition reaction, also known as a synthesis reaction, also known as a combination reaction. Demo lab number 6. So for this reaction, we're going to take a disaccharide sugar. Well, you know that glucose, kind of the basic sugar, is C6H12O6. And that's a monosaccharide, one sugar. But if we make a disaccharide, we're going to put these two, link them together. And so we would expect C6H12O6 plus C6H12O6. We should end up with C12H24O12. That should be our disaccharide. That's like sucrose, as in the usual table sugar. Mom, please pass the sugar. That should be C12H24O12. But there's something interesting. When these two bond together, there's something called a dehydration synthesis reaction that occurs. And so an OH from one of these and an H from another one get taken away. So we lose an H2O, H2O. All right, we expect C12H24O12, but a water actually goes away as these two are linked together. And so we end up with a C12H22, O, 12 minus 1 is 11. So that is our disaccharide sugars formula. Let me show you what sucrose looks like. It looks like sugar. There, we'll just put quite a lot in here. How's that? About like that much? And the next thing I'm going to take is some stuff called sulfuric acid. Now you know sulfuric acid from your flashcards. Look at that nasty old bottle. Sulfuric acid. How do you remember the formula? Well, my favorite poem in the whole world. Little Janie was a chemist. Little Janie is no more. What she thought was H2O was H2SO4. Sulfuric acid. Woo. All right, so we're going to take some sulfuric acid and we're going to add it to the sugar. So our formula is going to be C12H22O11 plus H2SO4. And we're going to see if this reacts. Or maybe it won't react at all, because pretty soon we're going to see some reactions that don't occur. So, I'm going to use a stir rod, and I'm going to add some sulfuric acid to this, and just see if a reaction does indeed occur. Put the top back on right away, because that is nasty stuff. That about killed me a couple of years ago. I was not using safe technique in the lab, or in the back room. And boy, the fumes got to me pretty badly. All right, so there it is. Isn't that just incredible? Reaction occurring? Well, not much, is it? That's pretty boring. So let's see if we can go ahead and balance this. We now know that nothing happens during this reaction, so let's see that so let's take a look at what could happen. Wait a minute, what is going on here? Oh my goodness, that is a nasty sulfuric smell. Whew. Thank goodness we're in the fume. What is going on there? It's disgusting. What is that thing? I don't know what it is, but it's horrible. Oh, it just keeps coming out and coming out and coming out. Let's see if we can figure out what that stuff is. It's horrible. Phew! This reaction takes C12H22O11 and reacts with sulfuric acid, H2SO4. Little Janie was a chemist. Little Janie is no more. What she thought was H2O was H2SO4. And it makes carbon, just pure carbon. And it also makes carbon dioxide, CO2. And it also makes water. Let's see. I'll put them in order here. It also makes water, H2O, and sulfur dioxide, SO2, which is named sulfur dioxide, indicating that it's a molecular compound, SO2, and it also makes oxygen. And that is something that I forgot. I did not add this to your worksheet, so if you could please add oxygen. All right, so it's time to balance this. So you should pause the video right now and try to balance this all by yourself. It takes a while. When you're done, you find that the coefficients are 1, sucrose, 2, sulfuric acids, 11, where is it, 12? I think it's 12. 12 carbons, 1 carbon dioxide, 13 waters, 2 sulfur dioxides, and only 1 oxygen molecule that are made here. So this is crazy. So this is a really cool reaction in which we have 2 very large compounds that are being broken down into a bunch of small compounds kind of at the same time. So that's really 2 decomposition reactions occurring at the same time. Okay, and so that is reaction 6. Thanks.